the weekend. Yeah.
All right, we are live. Good evening or good afternoon, Tim, and good afternoon, rest of the
We
world
are live.
community.
Good evening or good afternoon, Tim.
Hear an echo from the Twitter stream, which is online now too. My name is Tim Vogels. I'm an associate professor at the University of Oxford. Today I'm hosting Tim Lillicrap. Also an associate professor, I suppose, at the University College London and a senior researcher at DeepMind. Tim Lillicrap is actually an alumnus of neurotheory from a long, long time ago in Oxford. So he gave one of the first talks of what was then a very new initiative for us. In March 2014, he talked about feedback alignment, very early preview into what would become a very well discussed and liked paper that still carries on to bear fruit, I think. So that was 6 years ago. Since then, Tim has worked for DeepMind and worked on various now very famous papers too. None of them maybe as nice as the feedback alignment for me, but for others they might differ in opinion. In any case, it's a pleasure to have Tim here today to talk about what has happened since 6 years ago. And Tim actually asked me to stop him from time to time to break out of the lingo of ML and into the lingo of neuro. And I'll try my best to do that. You can support me in doing that by asking the dumb questions, quote unquote dumb questions, that I should ask in the chat bar, and I will then open my mic and ask those to Tim. And the more complex questions you can, of course, as always, ask via the question box. And if you put an on-screen tag into your question, and I'll also invite you to the screen afterwards. I think that's it. Follow us on Twitter and enjoy the last seminar of the week, live and direct with Tim Lillicrap. Tim, the stage is yours.
Cool. Hey, it's always really spooky. I still haven't gotten used to it, talking to the sort of like non-visible, I can't hear anyone. I don't know. Anyway, so yes, for multiple reasons, it'd be great if Tim can get a couple questions in and things like this. Yeah. Okay. So I'm gonna kick off. I think, like as Tim mentioned, I'm gonna be kind of pretty machine learning focused for something that's neurotheory.
Share your screen. You have to share your screen. So.
I'm sorry. I thought it was ongoing. Sorry. So I will have another go here. I thought that you might be able to see it already. Apparently not. Can you see it now?
Yes, we can, and I'm going to focus on it right now.
That is a start. That's a start. Great. So yeah, I'm going to be kind of. So some people can see my screen. Okay, it's just you, Tim. Don't know what's going on. Yeah, that's fine. So I'm going to be kind of fairly sort of focused on machine learning stuff today, but I want to draw bridges as I go to neuroscience, and I think that it's maybe I think it's always been the case, but I think maybe it's increasingly interesting to sort of try and look into what's going on in the machine learning front and see if there are things that might there were lessons that might be learned for sort of how we think about neuroscience and how we do computational theory in neuroscience. So I'm gonna kind of try and do this as an outline. These are just sort of roughly what I'm going to try and lead people through. I'm going to try and situate this question of model-based learning in neuroscience a bit, and I'm going to then kind of talk in. I'm going to kind of go through some of the basics of reinforcement learning and sort of deep reinforcement learning. And talk a little bit about where the field is now. I'm going to try and get a bit of understanding about what people mean by model-free versus model-based reinforcement learning. And then I'm going to describe two recent algorithms that I've been involved in working on in the model-based reinforcement learning sort of domain, which work in the context of unknown environments. So environments where you don't know ahead of time how they operate. And I'll tell you what that means exactly. But I think these are then algorithms which are much more interesting as far as neuroscience. I mean, most animals and humans, we kind of enter into environments that we don't sort of know in detail. And we need to work with them and operate in them. And then I'm going to discuss some of the insights and limitations of these approaches, where the field might go next, and where there are kind of some bridges with neuroscience. So look, let's just start with this picture, which I think is probably familiar to many people. But this is the sort of what I spend a lot of my life thinking about, is this kind of sort of the basic picture of reinforcement learning, where you've got an agent who's going to take actions in the environment, gets observations, sort of sees some aspect of the environment, and then gets reward and wants to get as much reward as it can. And you know, this sort of thing is really quite different, I think, from things like supervised learning, in the sense that for example, let me just see here. I'm just trying to get Tim in my picture so I can see a human and possibly their reactions. So you know, supervised learning, which is I think the thing that many people are most familiar with as far as machine learning. You've got some sort of fixed data set. You're going to try and classify or regress that data. Reinforcement learning, I think, differs in a couple ways, but one of the biggest ways is that the data depends on the actions you take in the environment. So that data set that you're working with is growing or changing, and that's really fundamental to RL, and it makes things much trickier, much more painful. And I think I'll try and make some ties back to this notion when I talk about why I think it's been traditionally difficult to make model-based algorithms work. So just sort of have that in mind. I want to make here a little comment on Jan's cake analogy, which I think is probably familiar to many. So Jan, I think, sort of now somewhat famously or infamously had this picture of this big cake, and you know, in this picture, I guess he would say that self-supervised learning is really where sort of an animal or a human is sort of getting most of the bits that make up learning. Then maybe it's doing a bit of supervised learning, the icing, and then reinforcement learning is just this cherry on top. So there's just a few bits that are being used to kind of tune the other parameters in, say, one of your big networks to make things work. And I actually agree with almost all of this analogy. I think it is correct in the sense, likely correct in the sense that in terms of the sort of order of magnitudes of the bits that animals probably use, so that is that most of the parameters in their big networks in their heads are coming from sort of unsupervised or self-supervised learning. They're doing a bit of supervised learning in a sense, and then you know, how much is real pure unsupervised learning? Maybe it's relatively little. But I want to say, I think that the picture is totally wrong in the sense that the reinforcement learning, you know, solving tasks in the world is really the whole point. So I think in that sense, the picture misses things entirely, in that the reinforcement learning is sort of like the sort of actually getting the job done, and sort of supervised learning and self-supervised learning that you might do is really all kind of there to support it, right? So in that sense, I think the picture is a bit funny and flipped, and I guess I have that in mind as I go into it. Okay, as far as a sort of a neuroscience, sort of situating things a bit in neuroscience, you know, neuroscientists have for ages and ages been interested in the idea of reinforcement learning, and also this idea of model-based reinforcement learning. So building sort of internal to your head some model of the world and leveraging that to perform well, to do reinforcement learning well. There's a paper, so I was digging around thinking about this talk. There's a paper from 2012. So yeah, it's getting on 8 years ago now, by Nathaniel Dawes' group, and I just want to read a couple of sentences from this because I think it'll sort of situate things as I go through this. So he's saying the reward prediction error theory of dopamine function has enjoyed great success in the neuroscience of learning and decision making. This theory is derived from model-free reinforcement learning, in which choices are made simply on the basis of previously realized rewards. Recently, attention has turned to correlates of more complex, albeit computationally complex, model-based methods in the brain. These methods are distinguished from model-free learning by their evaluation of candidate actions using expected future outcomes according to a world model. Puzzlingly, signatures from these computations seem to be pervasive in the very same regions thought to support model-free learning. There's kind of two things I want to say about this. I think that we're going to see, two things to say about this. I think at the time of writing of this, we really had no good examples we could point to of model-based algorithms that really worked on hard problems without having access to a sort of a perfect model of the world. So that was really missing at the time. And now that we're starting to sort of see some of those algorithms arise that are functional, I think we can begin to point to lots of reasons why this puzzle may be explained quite easily by just like how these algorithms kind of quite naturally work. So that's where I'm going to kind of one of the things I'm going to tie back to. So okay, so I've told you what RL is. What's deep RL? Deep RL is just, I'm going to have some network or set of networks that make up my agent when I do this, when I do RL. And I think there has been a profound shift. Reinforcement learning as a discipline has been around for decades, was really sort of, I think, well formalized in the 80s in some sense, say in Sutton and Bardo's book. But the advent of getting big, deep function approximators to work has been revolutionary to the field. So the sort of first example of this, maybe that people know best, is this sort of playing Atari with a deep network. So this was some work from Vlad Nee. And basically he showed you could take a big, deep convolutional network with, in this case, Q values that it was approximating. You could train this thing and get it to perform pretty well on a whole bunch of Atari games, just looking at pixels and getting rewards, right? And I think, so Tim, just so I have a sense, I'm going to bug you for a question within 2 slides. So just a prompt. I just want some kind of anchor. So just in the next 2 to 3 slides, something. Yeah. Okay, so I'm going to make now a bit of a bold claim, which is that as far as the current state and limitations of sort of reinforcement learning, I think we've kind of entered into a moment now, which is sort of was, unthinkable from when I was a PhD, which is I think that we can, for any sort of single task or problem, where we can formally specify and query a reward function for that problem, and we can do some sufficient exploration and collect lots of data, I think we can basically solve it with the sort of methods in deep RL that we now have, which is a kind of a crazy situation. Maybe one of the best demonstrations of this for me is recently with this work with Dota and StarCraft, which are both games that video games that people play, and both of them in some sense have the whole sort of sensory motor and high level decision making pieces. So it's kind of the whole package. People who play this, they spend 8 hours of their day getting good at it, the top pros, and they really execute both at the sort of high level thinking and at the low level kind of micro control sensory motor loop level. And we have demonstrably recently solved these kinds of problems when these conditions are satisfied. So it's kind of totally remarkable. I'll show you some other examples recently. So what then remains challenging in deep RL? I think that there's 2 main things that I would point to. One is learning when reward functions are difficult to specify. So in games, things like this, we can write down a reward function on a computer, we can query it, and we can use that to get better and better. And I think a lot of the things that animals and humans do, it's very hard to write down a reward function. So that's really tricky, and I'm not going to talk about that much today. And the second one is the one that I think most often is pointed to when people think about deep networks and so on, that is data efficiency, multitask, and transfer learning. So these are things that we think animals and humans in many cases are still doing much better than some of the algorithms that we have. Tim.
Actually, I wanted to ask like before the last two slides. So reinforcement learning has a biological parallel, right? Does that parallel hold for deep reinforcement learning, or are the number of layers just way more? Or in other words, why does the computer start beating the human performance? What do they do better than the humans? And how could you make the human more competitive? Like, what would you have to add to a brain to make the human more competitive?
Yeah. So so specifically, I guess maybe. So yeah, lots of aspects there. I think there's so let's say specifically in the StarCraft case. I mean, maybe let's take that example for a moment, where now it is true that we can sort of produce players that will beat top human pros in matches. I think that there's a whole sort of set of differences, and humans still maintain some advantages. So, for example, I think adaptability on data efficiency. So if a really top pro gets to spend some time playing against an algorithm enough, they can potentially adapt quickly enough that they'll start beating it. I think on the other question, this question about sort of like size of network and things like this, yeah, I think it's actually clear that we're in deep learning, in some sense, we're probably already working with networks which are much larger, or at least much deeper, rather, than some of the ones that human or animal brains are running around with. I think that there are parallels. So let me take the most obvious one, which is, people do vision networks for classification, and some of these networks have 150 to 200 layers. So this is kind of becoming standard in ResNets setups, is you have just networks that are giant in that sense. And I don't think that it sort of seems unlikely that even if you squint, you could see there being that many sort of physical layers in something like Cortex. So the question is, what's going on there? I think that there is, and people have drawn this parallel a bit. There is a parallel to draw between many layers in a feed-forward sense versus many layers in a recurrent sense in a human brain. So you have this like 200-layer network in a residual network. You could maybe think of it as similar to basically ruminating further in time on the same piece of data. And that's usually how I would sort of think about the connection on the depth question, for example. Yeah. Okay. So yeah. So the red, this point number 2 is the one that I'm going to maybe think about a bunch, and specifically, the hope I think for a long time has been, maybe. Why not plan with a model, right? So I'm gonna run through quickly some of the sort of older school model-free stuff, which has really worked in the last little while for us, including in games like StarCraft. But this is a question that I get all the time, or had been getting for years. Why not plan with a model? Why not use models? Won't they give us data efficiency? Can we not use them then to spend compute for performance? So think longer to produce a better move in the environment, and then maybe also generalize and transfer better, because I sort of already know how the world works. And so as soon as someone tells me about how to obtain a new reward, I can already reason about how to obtain that reward by moving through states in the world. So it should give us all these things, right? And so people would often ask me this, why don't you work on this? The reason, actually, for a long time is that models in unknown environments in particular have been a real pain in the butt, and it's been hard to make them work as well, even as well as model-free counterparts. So that's the truth. So there's been many, many failures in some sense. It's only been recently that we've started to see recipes for algorithms that are working well for models. And why have learned sort of algorithms that incorporate models and plan with them, why have they been tricky? I think we don't deeply know, but I will conjecture that one of the issues has been this. So why is it dangerous to plan with a learned model? So you get some data about how the world works. You ingest this into a model which sort of in your head, which is like, okay, this is how I think the world works when I push on it. Well, planning is inherently a maximization operation. So I'm looking for sequences of action that make my expected returns better. And planning operations, therefore, will go out and search for, in your model, imperfections. So we'll search for and exploit imperfections in the learned model, and this will lead to disaster generally. So I think that's actually been at the heart of why learned models, algorithms with learned models, have tended not to work very well. And we've been working with model-free stuff for a while. And I'll come back to this point. Tim, do you have a question?
Yeah, is that because we're not able to make the model flexible enough, or I don't quite understand why that is.
Yeah, so I'll show you in a moment. I'll show you what I'm going to do is I'm going to walk through two pieces next. I'm going to walk through some of the model-free stuff very quickly to get us back in that on that page. Also, the components to model-free stuff we're thinking more and more important in general. But basically, you can think about it like this. I mean, a model of the world is really trying to capture something quite rich, like how when I move my arm, for example, right now, I mean, that's causing, when I make that simple motion, all sorts of sensations across my skin. It's a very complex kind of thing that I'm predicting, much more complex than predicting a scalar reward or value. So there's all this richness in the world. I'm trying to make predictions about that, and if I only have limited data to do that, then it's quite easy for me to build models that have holes in them. And actually, here's a way to think about the holes, right? So everyone, I think, or many people at this point have heard about these adversarial examples or attacks in deep networks, right? So that is, there are ways to fool them. Well, if you think about a planning operation as something that is, again, like basically it's attacking your model. So it's attacking this model and it's saying, can I, I'm gonna run this model forward in my head and I'm gonna try and get the most reward I can. And I'm specifically looking for places where that model delivers crazy high rewards. And so in some sense, like the whole planning operation is almost sort of like adversarially attacking your own network. And that can be, that can be difficult to deal with, basically. So does that help a bit?
Yeah, I think so.
Okay. Okay, maybe some specifics will help a bit. So let's remember DeepRL.
Someone asked just now, if planning can search for and exploit intersections, could this be used adversarially? Is that currently a topic of research?
Intersections. I mean, in short, yes, there is some ongoing research where people are using, if you like, sort of planning like operations to sort of bring adversarial attacks to various kinds of networks. Maybe I'll come back to that. I'm not sure quite what's meant by intersections, but yeah, I think the answer is roughly yes, from what I can gather. Yeah. Okay, so a tiny bit of notation, right? So this here is sort of my policy, which I would produce an action from given some observation that I see S. send that action to the environment will advance according to some probability, sort of to the next state in time, given a state and action. Is this thing showing up here down here, this annoying bar for you?
Yeah, it comes back every time you move the cursor and it goes away.
That's annoying, isn't it? Okay, let me try this. Okay, that's pretty awful. Okay, and then I'm going to turn off the pointer. Maybe that's it. That would be ridiculous. But so then there's observation here. ST coming back into the agent, and it's also receiving rewards R. Okay, so
now we can't. Oh yeah, we can see your cursor. Yeah.
Okay, good. Yeah, somehow it's the okay. Okay, so then and here's kind of then the sort of simple way that I conceive of this in general. It's good to have in your head, So then a brain is kind of like this policy network, which has a bunch of parameters. Say the weights in network, which I'll lump together in this case into theta, and so then I can think about a policy pi of theta, which gives a distribution over actions given some observation, and I would then sort of sample an action from it and push that action out to the world. Okay, so here's a single trial of RL, and I'm going to kind of burn through this pretty quickly, but I think this part is in some sense relatively straightforward. So, then what does a single trial of reinforcement learning look like? It's sort of starting in some state. I compute then with my policy network some distribution over actions. I sample an action, I get a reward, and then I repeat this process. So then I push that action into the world. I arrive at a new state. I compute a new action distribution, sample, get a reward, and so on through time. I can think about, for example, the probability of a particular trajectory in the environment, tau then, as being computed like this. So it's sort of the probability of being in some state, and then moving through this sequence in space-time, according to the probability of taking actions and taking transitions. This is really annoying with this. I'm sorry. I'll try and just keep my pointer out of the way as much as I can. So then, when we measure actions, when we measure outcomes, we're really thinking about, okay, I want to maximize return. That's what I want to do. I want to get as much reward as I can in the environment. So then my objective function would look something like this, where I say it's really sort of parameterized by all the parameters that live in my action function, my action network, my policy network, and so the probability that they give to particular trajectories through the environment, and then the return that's associated with taking that trajectory through the environment, integrated across all the trajectories. And then I guess possibly the simplest way to kind of come into thinking about how I would then do reinforcement learning is just with something like a policy gradient, which you can think of as kind of the analog to supervised learning, but for reinforcement learning. And then there's some issues with the data stuff, but this is basically it. 2 steps. I would sample a trajectory by rolling out the policy. So I roll out the policy through space-time. I get a trajectory, and then I compute a gradient of that policy gradient that I just showed you with respect to the parameters in the network, given that trajectory, and that will be unlike the sort of supervised learning gradient. It will be like very stochastic, dependent on the actions I take, and things like this. So it will be very imperfect. It will be just an estimate of the real policy gradient. But if I take a step in that direction, on average, I will improve my policy. So many of the modern model-free algorithms have ended up looking something like this, quite simple, having 2 basic pieces then, which I'll go through in a bit of detail now. So you would have a network here, which is taking these observations and computing a policy, and then they would compute one other function, which is this value function, which is going to help you produce a better policy gradient and improve more quickly. So it's worth digging into what this function is for a moment, and I'll walk through. So there's basically two expressions here which are used to update these two pieces. And actually, let's look at this policy gradient part first. So this is how I update the policy head, and in effect, I'm saying here this is the log probability of an action under my policy, and I'm going to basically, in some sense, increase the log probability of an action under my policy according to how rewarding it was, right? So how much return I achieved there. So if I achieved lots of return by taking an action like that, then I would increase the probability of that action more than others, okay? And so then there's another thing, this other piece that shows up here, which is this, this value function. And that really is important because these policy gradients are very noisy, and we want to make them as noise-free as possible. So we use this value function in the following way. So first I'll define it, and then we'll talk about what it is. So this value function basically says, if I started in some state s at t, and then, for example, I followed my policy, my current policy pi, then how much return would I expect to accrue from that state till the end of the trial, right? So that value function is trying to estimate how much return I'll see starting from that state and executing my policy. I look at this difference, and that difference actually is what I use to train my value function here. So I'm actually trying to train it to get better at predicting the kinds of returns I'll see under my policy. And then I also use this difference to compute an advantage. That's what this thing is called, this advantage actor critic. I compute an advantage, and that's basically, in some sense, this is what I expected to get from that state. This is the return I actually got from the environment. And so if I got more return than I expected, then I will increase the probability of that action more. And if I got less return than I expected from that state, then I'll decrease the probability of those actions. Right. So these things, these model-free algorithms, this is sort of the basic form of many of the model-free algorithms we've recently seen, and they're surprisingly powerful. So this was one of the early examples of things that we did with these kinds of things. This is an agent that, again, from pixels and reward, has learned to navigate around an environment and pick up these apples. And initially, when it's randomly initialized, it just bumbles into walls. It has no sense of anything. And actually, when we started running these experiments, I think there was very much a sense that like none of this was going to work. But actually, as you can see, it works pretty beautifully. So this thing's pretty decent about having a sense of how to move around. The downside here is it takes, a huge amount of data to make this happen, a huge amount of data, and in large part because the policy gradient has high variance, right? Just to give you two more quick sort of versions of recent things that people have done with policy gradient algorithms. These things are truly kind of amazing. This is another policy that's been learned with model-free policy gradients. So pretty cool stuff. Looks pretty wacky. But then, again, sort of now in 2020, you can take these policy gradient algorithms and do some pretty mind-blowing things with them. So this is not animation in some sense. I mean, obviously it's being animated, but this character is really sort of the neural networks behind this are really controlling torques into this body, and it is really controlling the physics. So in that sense, it's not just an animation. It's really doing these controls. And the main downside here actually is basically the data efficiency in some sense. Tim, do you have a question?
What do you mean with data efficiency? The number of times you have to run this to train it?
That's right. So it's sampling the environment many times. Yeah. But you can see as far as the sensory motor behavior. So this is also, I should say, this case where it's catching, this is all done from vision as well. So this is the whole sensory motor loop, if you like. This agent really sees what you're seeing on the left here. So it's catching this box. It's catching objects that it's never sort of worked with before. It's trying to put them in this box. And this is learned with a policy gradient. Yeah. So kind of
on the point of view, not on the on the left half of the screen. It's trained.
That's right. That's right. So yeah. So it really has point of view where it's in the eyes. Like it basically has cameras in the eyes of this thing that it learns from, and then it has it has proprioception as well. Yeah.
Someone just asked what distributionally robust means.
What does distributionally robust means? Okay, so in this case, I think it was this text down at the bottom. I think it's just referring. It's referring to the fact that it can use. It can experience and work with objects that it hasn't seen before. So it's sort of like if the objects are bigger or smaller than it's seen before, and so on. It is not simply memorized a policy, right? It has something which is robust to those kinds of things in this sense. Yeah. Okay, so like I guess one of the points being you can do some amazing things with even model-free reinforcement learning, but maybe they're not as data efficient, and maybe they don't give us this ability to trade compute for performance. And so I'm going to head into talking about like model-based stuff now properly. It's worth saying model-based stuff has been around for ages, and in cases where you have a perfect model of the environment, people have since 2012, for example, had some amazing model-based algorithms. So this is behavior that is executed in 0 shot. So basically no data in some sense, because you have so this is work from Igor Mordach and Emma Todorov, where they're sort of doing these behaviors because they have sort of a perfect internal model that they can differentiate through. So if you have a perfect model that's sort of unexploitable, we kind of know you can do remarkable stuff. This is kind of cool in that way. The other piece that we've seen and that I was involved with, and I'm going to use it as sort of a way to build to these other some of these other model-free algorithms, is some of the work with AlphaGo. And AlphaGo combined, in some sense, three pieces together to go and play Go at top level. So it combines a policy network, which we've already talked about, with a value network, and finally with a model of the environment, and in particular a perfect model of the environment. So AlphaGo uses an exact implementation of the rules of Go internal to its head, right? Okay, and it plans with it. So what does that look like? So just very quickly, this part is sort of just building to where I want to go. There are some initial parts in AlphaGo where you train a policy network and you train a value network, right? So these were initially derived from human positions and from self-play. So you produce these networks which would predict moves and then also predict the outcome of games. So those are what these two pieces do. Notably, I think it's worth mentioning, deep networks make a huge difference. It's just worth kind of mentioning along the way. You can't really do this with small networks or shallow networks. These things make a huge difference. And in particular, you can see that basically even small amounts of training accuracy difference end up with huge differences in win rates. So even if you're like, you talk about a % difference in terms of your predictive ability, has massive effects in win rates. Okay, so how does AlphaGo kind of operate? It does the following. It uses a planning algorithm called Monte Carlo tree search, which in effect looks like these kind of 4 steps. What it does is it sort of imagines moves in its head, and it does, first of all, what's called selection, which is it descends down this tree by looking at what its predicted, the sort of predicted Q value, or the value of this action is, plus an exploration bonus. So it sort of descends down the tree. When it sort of gets to some point in that, at the leaf, it expands that. And in particular, it uses the policy network to guess what are the most promising moves from that point. So that's what the policy network is used for. And it also evaluates that node. So it basically computes the value function for that position on the board and tries to think, this is the likelihood I'm going to win. And then finally, it backs those up to compute new Q-value estimates, which it will use in future in its internal model. Tim, did you?
Yeah, I was just wondering, for those of us who don't know, I'm one of them. How does that compare to the strategy of Big Blue, or whatever the IBM computer was called, that beats the chess masters?
Yeah. So this is Deep Blue, and I genuinely actually something I'm not an expert in. It used more traditional. So there's two things, I guess. So it used a different kind of tree search, but still sort of a forward mode tree search, sort of alpha beta kind of tree search. And maybe one of the biggest differences was that was based on human evaluations. So whereas in this tree we use a learned value function, in effect the chess engines are based on sort of like tuned up human evaluations for board states. And that's maybe the biggest difference there. Yeah.
And do you know if how far ahead do human players look?
So in chess, so it depends. Oh, sorry. You cut out for a moment. You asked how. Yeah, we got a bit of delay. You asked how far ahead do human players look? Is that right?
Yeah.
So the answer, I think, is sort of, it depends, of course, on how expert they are, but like 6 or 7 in chess. And then in Go, it's thought to be a little deeper, but in part because certain sequences in Go tend to be more like given, something like this. Yeah.
And AlphaGo, how deep do they think?
Yeah, so that's a good question. So AlphaGo was able to search really deep, right? So but I think maybe it tens, certainly like tens or even like hundreds of moves. There is actually something worth saying here, which is that the number of move evaluations that's used in AlphaGo and some of the descendants that I'll talk about was orders of magnitude fewer evaluations than what the chess engines typically would have used. So the expansions in the old school chess engines, was like on the order of millions and millions and millions of moves. So quite different in that sense. Yeah. So, okay, so this stuff works. I'm not going to belabor this because I want to sort of push on to some of the newer stuff as far as model free goes. This stuff works. AlphaGo really does perform well and beat humans. You can do this without human knowledge, which is maybe interesting. So you can basically derive your policy functions and value functions from just self-play. So you can basically set up 2 computers that play themselves, look at who wins the games, and run basically the whole AlphaGo business just from self-play. And this stuff can still work, and indeed can get up to performances that are comparable to the best versions that we ever produced using human data. As well, these things can work across a variety of games like chess, shogi, which is like a Japanese style chess, and Go. So this is actually, to your point, this was Tim. Here, this green line in chess is Stockfish, which was the best previous player. And AlphaZero actually can beat it. And I think actually the descendants that are now winning the chess tournaments are effectively based on AlphaZero, that style of play. Okay, so now I'm going to move into one of the new algorithms that I've been involved with, which is this MuZero algorithm. So all of the things that I just described, AlphaGo and AlphaZero, use perfect models of the environment. So that is, they have a perfect copy of the games, and when they make those tree searches, when they develop those tree searches, every step in those tree searches is according to the rules of the game that are known perfectly. So instead, what you can imagine is trying to build a model of how chess works or Go works. And one of the lessons that I think we've learned along the way in trying to do this is that the sort of traditional conception of how to build model environments, like internal models, is probably not the best way forward. So that is, traditionally we've thought, okay, what you should do to build a model of the world is explicitly go and try and model how transitions of the world work. And MuZero, as you'll see, focuses on something different, which is building a model which lets us predict future reward, value, and policy. And these are the essential components that you need for something like MCTS to work. And in fact, MCTS doesn't really care ultimately what the state of the world is. It just cares about these things. So how does that work? Okay, so it works in effect like this. So this is sort of a board state you're in. And this is, in some sense, then a representation of the MuZero search tree that's built. And so all of these transition functions between sort of imagined moves, the G's here, these are neural networks, right? And then from each of these neural networks, you produce a reward prediction, a policy prediction, and a value prediction. And so you can run MCTS, but every sort of node in your MCTS tree is kind of the output of a neural network from which you can produce the predictions that you need to run the algorithm forward. In MuZero, this thing basically acts exactly as AlphaZero would. It builds a search tree. It looks at the distribution of the moves created by MCTS, and then it just picks one of those moves and carries on forward. And this is maybe another way to visualize it. This is how it's trained. This is how it's trained. So you can imagine that here you start in a state, and you're going to roll forward and predict policy, value, and reward. And notably here in this picture, what you're feeding in as inputs to the model are the actions that you took. But actually, these pieces, the state, is basically ignored, right? So the future states of the board that you happen to have gotten into are not fed into the learning process. So this state is, but then you just unroll given the actions that you saw and make these predictions, and you just say, whatever happened to the states, I'm not particularly bothered. Yeah. And the sort of main result here is that you can recapitulate effectively the AlphaZero results, and you can apply this to domains like Atari, where you wouldn't sort of necessarily have a perfect simulator available to you for the rules of that game. And you can apply the MuZero algorithm in sort of all of these contexts and recapitulate the results as if you had a real simulator. So in fact, actually, one of the things to say here was that we were even able to push this to the point where you were able to beat some of the strongest model-free algorithms at the time on things like Atari, right? So some of these environments. There's a couple of other differences that these algorithms needed. I'm not going to dwell too long here because I want to cover one more piece. But basically, you need to incorporate ideas like there are rewards along the way, and you need to sort of normalize those rewards so you can plan effectively with respect to them. So that is, if in board games, you know that all the rewards are either -1 or 1. But in many domains like Atari, there are kind of rewards that come at you and they're new. You've never seen a reward that big, and you need to now be able to plan with respect to rewards that large, right? Plan effectively. And then this is really, I guess, the crux of things. We now then have algorithms where we can spend more time or seconds or compute and improve. So ELO is a measure of performance of the play of these things. So we can increase the performance of these networks with a learned model for many, many seconds, many, many evaluations by pouring in more time or compute. So this is really the hallmark of having a planning algorithm where you can leverage compute or time for performance, and you can do it in a case where you did not know the rules of the game. Yeah, which is kind of a cool place to be now. Okay, So there was, so that has been, I should say, that's been mostly on most of the work thus far on the MuZero front has really been focused on this question of how to leverage models to be able to pour compute into them to give you better performance. So it's like one of the things that we would hope for from model-based learning. Another project that I've been involved with, which is with this guy, Danajar Hafner, very talented grad student at University of Toronto now. We worked on another project which has been focused on using learned models for data efficiency. So really sort of trying to use them for data efficiency ends. But many of the same lessons apply. So that is the really important thing we think, the really important thing is building these models of value, reward, and action, right? So many of the components that just show up in model-free algorithms just show up in these model-based algorithms. And so now just recalling the abstract that I began with, there was a bit of this sort of tension about like, why would we see these signals in the brain that maybe look like model-based in these model-free areas? Actually, we are beginning to think that the distinction is very blurry. Tim?
Does MuZero perform at the level of AlphaGo?
Yeah,
Okay.
it really does can recover the same performance.
So one could argue that before, the model-based algorithms weren't performing as well, as you said, as model-free parameters, because the model basically was constraining the flexibility of the learning process too much, and sort of allowing only bending at certain joints when reality was, and then you're softening, like somehow you find a middle step here, right? Like where you allow for models to be soft enough, or I'm having a little trouble with the analogy of what MuZero does, because it seems like you're almost throwing away the model completely. I mean, could your critics say that MuZero is actually model-free, or?
Yeah, so it's a great question. I really think that the answer there is more that these things, the lines are blurrier than we kind of naively supposed, and actually I think it's probably the best thing to say is it's not really worth entering into that kind of a bun fight. It's better to look at just like materially at like what like exactly what do these models do, and these are model-free, model-based are kind of analogies. The important things maybe from the perspective of the model-based case was that you had something in your head which you could try to pour actions into, and you could try things, you could try out different sequences, and that you still have.
So it's basically a knob that allows for the flexibility of the model to change, right?
Yeah. And so I think we're going to see more and more of these kinds of hybrids, and it will be very interesting. Just on a time check, so I can now really try and maybe I should just try and do really a wrap up. And I have this sort of second algorithm, which I think is interesting, maybe more from the data efficiency front, but I could kind of return to it maybe in questions or something. So shall I just try for a wrap up?
Yeah, I think if you take another 10 minutes, 15 minutes, that wouldn't be an issue.
Okay. If we have 10 to 15, then maybe I'll go through this second algorithm a bit.
Sure. I think that. I mean, people are going to vote with their feet. If they're bored, they're just going to log off.
Okay.
But it seems so far we've got pretty good retention numbers. So you're not losing anyone.
All right. Okay. I think actually the nice thing maybe is that when I describe this one, I'll also go into a little bit more of the mechanics, and many of which are similar, and people might appreciate it. So this dreamed control algorithm, which is a bit of a funny name, but it really sort of breaks down into three pieces, and I'll lead you through these in turn. Basically, it learns a dynamics model of the environment from experience. This one in particular, and we'll look at this some more, does try and make a sort of prediction about you know, what's going to happen in future in terms of these observations. But I would say actually it is arguable, you know, how deeply important that is. And it's in fact, you can run the algorithm without doing that. So in some sense, this is an optional piece here. So okay, so you build, you gather some experience, you learn a dynamics model from it. You can then, in this case, learn behavior in imagination. So you can basically say, take your model, which you've learned, and run out sequences on it. And notably, you're not producing here, you're not producing predictions about what the world will look like. You're just saying, I have some latent state, which kind of has some very loose coupling to what the world is. And from that latent state, I can produce value, reward, and action predictions. And then from that action prediction, I can produce sort of a next action and a next latent state. And I can do these rollouts. And based on those rollouts, I can then improve my own value functions and action functions. So I'll show you a bit more what that looks like in a moment, but I can basically do a bunch of imagination, sit there and think for a long time with this imagination and improve my value and policy functions. And then finally go back to acting in the environment.
It's intuition more than imagination here, right? Because you don't imagine actually the future states. You're just like, oh, it might just work like that.
That's right. So you don't imagine, that's right. You're not imagining the particulars of the future states. That's exactly right. In order to do these rollouts and in order to do the behavioral improvements, you're not imagining the particulars of the future states. We do find, as I'll show you, that trying to constrain these latent green states by doing some prediction of future states, trying to sort of constrain those states a little bit is helpful in terms of data efficiency, but it's yes, those green states are a bit unanchored. It's sort of intuition in that sense, yeah. Okay, so in particular, just so you have a sense of where this was done. This was done in these sort of physics domains, like these kinds of ones you see, but only via pixel input. So you've got to control these things using pixels, or rather you see pixels, you produce joint torques, and you have to control these things, and as usual, you get, say, just some rewards. So, you know, what are the pieces of a model that looks like this? This piece, you know, looks like this, which is basically, there's a representation model, which is sort of producing these S's, the green states, these green latent states, from a previous one, an action, and an observation. There's a transition model that lets me transition through these green states without having an observation. So notably, this transition model doesn't need an observation. And then there's a reward model where I'm trying to predict the value of those states. Okay, so then I have two other things that are sort of added in here for the sort of behavior, which is, again, an action model. So this, I mean, we could call this pi, same thing as I've told you about before, and a value. Okay, so what do these things look like kind of in algorithm box format? You know, so just to make this sort of really concrete for a moment, because I think sometimes these algorithms can be a bit of a soup to think about, but just very concretely, you know, what do I do for an environment interaction? I just sort of reset the environment. I carry on for some t time steps. I compute this S at t, which is basically my latent state here from this sort of recent past history. And then I compute using my Q of A given S, an action. And I take that action on the environment using a bit of noise on it. And then I get back an observation and a reward. And then I basically just add that data, that sequence, into my data set, right? So that's how action happens. That's how interaction happens. Then my dynamics learning is basically I draw a short sequence. I draw a batch of short sequences that look like this: observations, actions, rewards. and I push them through my my model here, and then I basically just update it. I can tell you a little bit about what that looks like, but in effect, I want to predict rewards and sort of future observations to some extent. But there's various ways to do that. Okay, potentially the sort of more important part really looks like looks very similar to what we do in the model-free case again, which is that I basically have these two objectives. I want to improve. I want to improve I want to push the value up using my policy, and so I want to improve this, which is my returns. And in detail, we use sort of a reparameterization trick, and you can basically just optimize this this queue that gives actions that way. This thing looks very similar to what I showed you before, which is like a difference between sort of predicted values and real values. This one is a bit funny because this is sort of like in your own head, right? So you make predictions, and you sort of make predictions about what kind of values you're going to see, but actually use sort of evaluations in your own head. Okay, so you put these things together. This thing can actually produce some in some environments. So this is quite interesting. In some environments, this thing can make predictions into the future that are not so bad when you go and reconstruct from them. So this is a true rollout here in time, and you can see that for a little while in time. So true and model are roughly tracking each other, and then start to really break down completely at some point. And similarly here, they track each other for a little while in time, but then begin to break down and sort of become totally sort of separated. But I think, as I said, it's sort of besides the point. It's good enough to plan with, right? And in fact, and this is maybe the kind of crux of these things, by doing this, by basically saying, I'm gonna ingest some data, I'm gonna pause, I'm gonna do a bunch of imagined rollouts with my model, and I'm gonna sort of iteratively sit there and just like try and improve my behavior and my predictions about value inside of my head. I can achieve similar sorts of results. So this is Dreamer here versus a strong model-free baseline in this column, using about, so this is a wide variety of these physics tasks, using about 2 orders of magnitude less data than the sort of strong model-free baseline. This is really the crux of it. So I can, by building this model that I can sit there and think on in my head, I can sort of iteratively improve this behavior policy. So there's some things that sort of show in detail which pieces of this are important. I'm going to talk about one last thing, which I think is really cool. This is not work of mine, but was work with this other fellow, Danajar Hafner, that I worked with for the Dreamer work. And then I'm going to sort of start wrapping up. So this picture, yeah, this is from a very recent paper. And as I said, I'm not involved, but I think it's super cool, and I want to explain it for a moment. So the yellow lines here, so this is a bunch of tasks. The yellow lines here are the Dreamer. This is the one that we worked on recently, where you're basically doing reinforcement learning. You're trying to improve on these tasks. So these are returns. These are environment steps. So in this work, this planning to explore work, what they did was up until, so from this point on the graph to this point in the graph, hopefully you can see my cursor, they ran the Dreamer, but with no reward from the environment. So basically, there's sort of like, they get to see the physics moving, they get to push actions in, they get to see the images moving and so on, but there's no environment reward. Instead, during that period, what they're rewarding the model based on is if it can get into configurations which surprise it. So basically, they're saying, look for future configurations where I have lots of uncertainty, and optimize getting into those situations. So you can think about this like, you've got this physical body, now try and move it around and find parts of it that you don't know how it works. And then at this point in each of these figures, at this point in each of these figures, you then start getting real environment reward, right? So that's the moment where real environment reward starts. You get to have some real environment reward that tells you how well you're doing. And you can see this plan to explore, which is basically Dreamer with this exploration, this sort of exploration drive. Once you give it some real reward about the thing you care about, you see that it just snaps up really quickly. So in some sense, this is the green line in each of these, and it just snaps up really quickly. And the idea really here is that you've kind of built a model that lets you understand something about how the dynamics works. And so then when someone says, okay, now if you get into this kind of state, I'm going to give you a bunch of reward, you can immediately begin planning with respect to that and how to get into those states. And I think I finally want to sort of link back to this question about the Jan LeCun's cake, which is that I think, unsupervised learning is undoubtedly massively important. But actually, one of the things that I think we'll sort of learn more and more as we get into these algorithms is that there's a real coupling between reinforcement learning and unsupervised learning. So here, like it is an unsupervised learning algorithm that's being used to sort of say, find me interesting parts of the world and experience them. It's maybe an unsupervised learning algorithm that's taking that experience and shoving it into the weights of your network. But there's a tight coupling between these two things. Tim, you seemed like you had a question.
I was going to ask whether this is parallel to watching someone else play tennis and learn a model of tennis while they play it, and then once you're asked to step on the court, you're prepared. But I think it's different, no?
I mean, it would be
it has input. It's like as if you can ask a player to move around on the field while you're watching them.
That's right. Like the version you just described is an even more difficult one, where I'm learning something from a third-person perspective about the dynamics of this stuff, and then I kind of leverage those. I think I would kind of say maybe it's more like I give you a tennis racket and I let you muck around with it for a few days, and I just say like play with it and do stuff with it, and then I say, okay, now I'm going to tell you a game. And someone who's like felt the weight of it and understands various things about it is in potentially a much better place to use it. Yeah. Okay, so like I said, I'm just going to wrap up there and see if there are any questions, if we have any time left.
We have 60 questions so far. So yeah, you've got lots of questions.
Okay. So I think reflections, I mean, we've had trouble building model-based algorithms, especially for sort of unknown environments in the past. But these recipes are starting to work now. So they really are starting to work. At the same time, I think there's a lot to be understood about these algorithms and their relationship with model-free approaches. I think there's a sense in which we don't really understand why they're starting to work as recipes, although I'll give you maybe a conjecture in the next slide. And I think the other thing that's really exciting now is that there are, I suspect, a whole bunch of connections to be made to the neuroscience literature, especially with respect to the kinds of data that were mentioned in the abstract at the front of this talk, which is, you go and look at neural tissue and you see markers potentially of both model-free and model-based signals there, and really intermingled in various pieces of brain tissue. And why would that be? I think actually, it increasingly, I feel like it's because these things are not nearly as distinct and separate as we once kind of naively thought they were. They're really like the algorithms that are working well in a model-based sense look actually much more similar to a lot of the model-free things than we might have expected. Okay, so why do recipes work? This is a sort of final conjecture. I I think one of the reasons potentially is that we have just started using much bigger networks. So let me explain something, a couple things here. So, or try and explain what I mean with reference back to this idea that, you know, when you build a model and then you plan against it, you're looking for exploits, right? And so how do you prevent that from happening? Well, ideally, you have a model that is not overfitting, right? That generalizes well and robustly. If you have a model that generalizes well and robustly, then it's hard to sort of, it's more difficult to adversarially attack it, right? And find these weird exploits in it. One of the things that, and so when you're actually doing this training of a model, so I showed you in the dream to control stuff, you have this step where you train a model. And there's a question there, how much should I train that model? How long should I train it for on the new pieces of data that have come in? And actually, I think one of the weird, curious results from the last couple of years is that question of how much and how long to train a model, actually, it looks like it's easier for larger models. So I'll now sort of just look at this figure for a moment. So this is from a paper in 2019. There's lots of work about this now on this phenomenon of deep double descent. And what a lot of these works show is that so this is the like the size of a network. In this case, the width of a residual network on the x-axis. This is the sort of train test errors going on here on the y-axis. And in this regime, people call this sort of classical regime. You see the sort of exactly what we'd expect from normal statistics, as you will, that the train and the test error drop together. And then the test error starts going up and up and up and getting worse and worse and worse. So this is overfitting. And then after a certain point, and this is the thing that's sort of quite bizarre, if you just keep making your networks bigger and bigger, actually this effect of overfitting just tends to go away, right? So I think partly what's begun to happen with the recent model-based algorithms is that we've started building models using larger and larger networks. And I think this actually just makes it easier not to overfit, which means that when you sort of do a maximization process in your head with that model, you're less likely to end up in trouble. Anyway, so this is conjecture, but I think it's worth paying attention to a bit. And I'm going to really leave it there and take some questions.
Thank you very much, Tim. I'm going to give you some time to read through the questions and vote on them. Maybe a quick 30-second interlude for you guys to decide what you want to have answered. We have 16 questions. I don't know if we'll get through all of them. So let's see. In the meantime, Tim,
yes.
There was a question that I already wanted to ask you, which was for the AlphaGo as well as for the chess, maybe as well as for the MuZero. All of these algorithms are starting to outperform humans in the task of their choice. What if you try to keep the level of performance equal to that of a human by introducing more and more constraints? Have people tried that to look at what the biological constraints are that make it, you know? Or what if you punished for looking too far into the future? What if is there a sweet spot for the machine to not simulate 6,000 trials in advance,
right?
For example. So
I would say there has really not been much done in this direction, and probably there's. I mean, I think that the kind of mode of operation with a lot of the deep learning, machine learning stuff is that actually people, for better or worse, I think there are good things about it. People are so sort of performance focused that as soon as something works, there's relatively little effort expended on cleanup or understanding. And that's good in some ways. It's driving results, but we also really don't understand a lot of the things that have come about. And I would say there's been no concerted effort that I'm aware of to take kind of an AlphaGo style network and really try and compress it down into sort of asking it to do the fewest searches it could or something. I think it would be a cool direction to look in. Yeah.
All right. I invited someone on the screen. In the meantime, Michael, you'd have to accept in order to ask your question. Oh, reject it. So I guess I'll read the question out for him. If you think about the cost of mental simulation in biological agents, then Monte Carlo tree search does not seem a very attractive algorithm for biological agents, too exhaustive. Also, biological agents may have limited depth by search. Here's my question. Would Monte Carlo tree search be a comparable algorithm with what biological agents might be using?
Yeah. Okay. Yeah, I think this is a great one. So Monte Carlo tree search has a particular form where it's basically doing sort of forward simulation using these sort of small discrete actions of the environment, like these sort of unitary actions of the environment, like placing a stone. And I think it is worth saying, like humans at least, I think with animals it's more difficult to say what's going on, but humans at least really seem to have a whole bunch of flexibilities that are not available in MCTS. So one of them is that with MCTS or with humans, it seems like I don't have to plan just forward in time. I can do all kinds of things, like I can imagine a constraining state or a final state and then plan backwards in time from that. And so actually, that's one, that's just one of the ways in which human planning processes look quite a bit more flexible than Monte Carlo tree search. The other one that I'm quite interested in at the moment, and I think is very real, is that humans, it seems like, have the ability to plan over long time spans without having to think about the intermediate small actions. So even if they're planning forward in time, they're kind of jumping to points in time far away without having to think about the intermediate actions. Kind of with reference to the question, MCTS I think is like is by no means going to be sufficient to explain the kinds of planning operations that humans do. I think that the real question is this. So we have another piece of work from last year where we look at just using like big recurrent networks and seeing if we can kind of elicit planning-like behaviors from them, which is kind of the other way to go. It's kind of saying, forget about having this specific planning machinery. Let's just have a bunch of neurons with a bunch of recurrence and see if we can get them to be like a planner of some sort and leave them free to figure that out from an objective. I would say that kind of works. My take on it is that really the answer is going to be very much somewhere in between, that you want some structure like that's informing sort of how your search and so on is set up. But nothing probably nearly as structured as MCTS, which is sort of every step is delineated and designated, and there's very little freedom as far as how you break down a problem. So it's in between these two things, like a totally unconstrained big recurrent network, which in theory could represent any planning algorithm you want. And then on the other side, this very like particularly formatted, delineated planning process like MCTS. And sort of the in-between is where the interesting research is now.
All right. We have another question by Yangfan Peng, and he'll ask for himself. I just unmuted his microphone.
Okay, hi, great talk. My question is, so if you say that the human brain does not have 200 layers compared to deep learning networks, I was just wondering, what do you think would constitute a single layer in the biological brain? So like, would you say it's a brain region, cortical layers, single neurons even, or subcellular compartments? And maybe the follow-up question, like, how would one go about to determining such a question?
Yeah, okay. So very naively, I want to say kind of two things about this. I think in a very broad brush sense, I might think that a cortical area, maybe in some very loose sense, I might think of as sort of a layer in a deep network. But I think it's really important to be extremely open-minded about this stuff at this point, and not to get too worried about the specifics of those analogies. I think we just don't understand enough to be all that confident on a statement like that. So I think that's probably the most important thing. And then I think the question is, the question instead maybe should be like, do we really want to say, oh, like there's a strict analogy between like this kind of a layer in a neural network and like, this piece of tissue? I don't know how productive that is. I don't think it's the best thing to do. I mean, you can probably look up maybe a talk of mine elsewhere. In short, I feel like the thing to focus on is just, how does learning work in a brain? And how does that unfold in time? And specifically how those parameters are arranged and where they are and how they're updated, rather than a specific analogy to like the current trendy deep network. Yeah.
All right. I'm going to kill your screen, but thank you for coming online. Oh, lovely. Goodbye. Next question by Samuel Alvarez. What you're saying is that one of the failures of an agent that predicts return from a model is that any model of the world is going to have circumstances where it will predict unrealistically high return, and it's specifically these circumstances that any reinforcement learning algorithm will gravitate towards, that it will learn to exploit the weakness in a model to maximize this unrealistic reward. But could this be useful in a way to indicate exactly where a model is weakest?
Yes. Yeah.
So make it flexible where it's unrealistic in a way, right?
Yeah. So and in some sense, actually, there's a lot of details there, and I'm not going to get into them really, but this work that I just sort of gestured at the end, this plan to explore stuff, it's sort of along those lines in some sense. So it's sort of, you can imagine this. You can imagine the following kind of notion. You have a model that you built, and you can imagine sort of saying, if that model includes some way of gauging your uncertainty about your predictions, right? So if your model had some way of computing an uncertainty, not just a prediction, but an uncertainty about your predictions, then you could kind of adversarially attack your model and basically say, like, in some sense, maximize its uncertainty, right? And then if you say, okay, this sequence of actions leads me into a place where I'm really uncertain about what's going on in the world, then if I go and try and pursue those actions, I should find data which will help me make my model better, because that's where I was uncertain. And there are all sorts of complexity to this, I should say, this sort of basic story that I just told, because, for example, parts of the world can be irredeemably uncertain. So, for example, static on a television screen is kind of, I mean, it's irredeemably uncertain. And so you need to have sort of, so the simple story I just told doesn't work, totally straightforwardly. But there are nuances, but in effect, yes, you can imagine doing things like that, and I think indeed we'll see more and more algorithms that are of that form. Yeah.
Can you relearn a model? So can you train MuZero on Go and then start having it play chess and see how the model is warped by its breaking? So no one has really done that, just because it's funny, the way these things go. Just because at least for chess and Go, there is one, in some sense, one piece of information that is really given to these algorithms about the structure of the problem, and that is like the input shape
and the output shape. So they don't know how actions work. They don't know, but the inputs and outputs are the size of a chessboard versus the size of a Go board. Now, there is a really cool thing you could do, which if you had the compute to burn and wanted to try, which is like, look, you can represent both chess and Go instead of having their natural board states. You could just represent them both as a bunch of pixels. So you can just have pictures of a Go board and pictures of a chessboard, and then learn your models over those kinds of things and kind of see what you would get. Yeah.
I mean, there are games that are being played on the chessboard that are, I don't know what they are in English, but there is other.
I'm not sure Shoji. I don't know if Shoji is on this. Well, yes. Okay. Yeah.
You could do that short circuit, like you could do a little.
Yeah. Play and these things are these things would be. This is a great example of the sort of thing that would be great to study, but the movement in the ML community is sort of slow on those kinds of things.
All right. There's a few questions on this imagination or intuition. What's the criterion to stop imagination? I can imagine too much imagination without feedback from the environment can give you degenerate solutions.
Yeah, and that exactly. So that's absolutely right, and that is in some sense the sort of point I was gesturing at not particularly well, which is that. So you've ingested, so you get some chunk of data from the environment, and then you can start learning on it. And the question is, so this is actually I said I would tie this back to the beginning of the talk, and I didn't kind of hit this note. So this is one of the places where reinforcement learning is truly trickier than supervised learning. So with supervised learning, what do? You basically take your data, you cut it into a training set and a test set, okay? And if you get really fancy training validation tests, but you basically cut into these two pieces, you do a bunch of learning on your training set, and then you just check how things are going on your validation set. And you sort of say, if I'm starting to overfit, then back off, do early stopping, introduce regularization, things like this. Okay. So here's the really tricky bit with reinforcement learning. I'm getting new data in, and that new data, by definition, basically, looks different than my old data. So I can't establish a fixed validation or test set that I'm just checking against, right? And in fact, and you might think, well, look, maybe that new data that's coming in is only a small amount of data relative to the data that you have in the past. But that new data is in some sense the most important data, right? So it's not like you can just be like, oh, I have a bunch of old data, like I'll just form a validation set there. That new data is crucially the most important data you have, because it's literally how you're performing on this task now. So this question then about how do I get in this new little bit of data, how do I know when to stop kind of training models based on that new little bit of data? That is a deep and hard question. I would say there are kind of various approaches that you can take. So I'll mention one of them that I think I've seen used with some modicum of success, which is that when I'm making updates to a policy, for example, one of the things that people will do is use a KL constraint on their new derived policy to their old policy. So they'll basically say, when you get some new data in, try and sort of make your policy as best you can relative to that new data, but with the constraint that you don't look too different from your old policy, right? So that you don't run away too far from where your old policy was. And that's one of the things that people have used. And that way you can say, spend as much compute as you possibly can. So optimize as hard as you can, but the constraint keeps you from going too far.
Yeah.
Now, I don't think that that's a completely satisfactory answer, but it is an answer that people have explored, and I think with some success. But.
So last question, buzzword a few people have asked, generalization. So obviously, the direction towards sort of making models more flexible would be one where you can solve any given task or learn to generalize over multiple tasks.
Yep.
Do you have any thoughts on that?
Yeah, I mean, I'll point people to it's maybe it's worth checking out. I think actually this planning to explore kinds of direction is maybe is potentially one of the coolest directions around generalization, right? In some sense, what they've managed to show a bit of, and I would say again, this is early days, and there's many nitpicks you could have, but they're showing that you can learn something about a world and how a world works, albeit sort of small and constrained at this point. But you can learn something about how a world works that's kind of relatively detached from reward, right? So and then when reward comes along, when someone says, okay, now I'm going to start giving you a reward for this, you're in a place to sort of immediately begin generalizing into that context, because you know other things about the world. So I think that direction is cool, and I mean that is in some sense the promise of models. Like if I can have a model. So okay. Final note on this: model free is in some sense a bit of a funny term. Model free is just like you build a model. You're really building a model of how the environment will give you like reward, a specific reward. And so then model-based is kind of like, can I get a more general model of the world, which then when someone says, okay, this is this specific reward, maybe you're interested in it, you can begin to kind of latch onto that immediately.
All right. I think there was a follow-up, I guess. Specific question though. Task-specific latent models bad for generalization?
It's a good question. I would say that the answer is I would say actually we don't know. I think that the expectation is that it's not going to be amazing for generalization, but I think actually they might be better for generalization than we would think. And maybe let me spell out a specific experiment, set of experiments that I don't think anyone has done. It would be something like this. You take a MuZero model, which learns something about the rules of Go, but it doesn't learn like the exact specifics, right? It learns something about the rules of Go, and it learns something about how the physics of Go works, but not the precise physics. And then you say, okay, now let me change the rules of Go, right? So you say, let me change the rules of Go, and you say, okay, now you start learning from that experience. And the question is, how quickly does that model let you adapt? How much of the information that's in that model, that sort of latent, that task-specific latent model, how much of it is still good for letting you make predictions about this new case, where the world has basically stayed the same, but the task is different? I don't think anyone's run an experiment like that. It would be cool. I would predict that it's somewhere in between. That lots would generalize, but not everything.
All right, thank you, Tim. Long Q&A session, but I think we should cut the cord here. Thanks again for coming. Thank you also to everyone in the audience. Thanks for staying for so long, and hopefully see you again next week with another neuro theory talk on worldwide neuro by Surgeon Stojic next Friday at 2. Until then, have a lovely weekend. Stay safe and sane. And goodbye, and I'll see you on the other side, Tim.
Yeah.
Bye.
See you soon. Bye.